So today, good morning all. Today we are going to discuss about the numericals related to the demodulators. Whatever the demodulators we have gone through in previous classes, such as square law demodulator, envelope detectors, and a few more detectors we have read. That is about squaring loop detector, as well as envelope detection, squaring loop detection, then square law detector, and diode rectifiers. So depend upon these four demodulators, what we have seen, according to that few numericals we are going to discuss. In previous class, in one video, I have discussed the numerical regarding the square law detector as well as coherent detector, that I was missing. So depend upon these two, few more detectors. Last class what we have discussed, like envelope detection as well as squaring loop unit is there. If there is a phase difference, what will happen to the received modulated signal which is to be demodulated, what will be the effect of those phase component, that we have seen in the previous class. So related to that, we are going to discuss for envelope detection and few questions related to the coherent and square law demodulation. Okay, so first question I am going to discuss, that it is related to the envelope detection. Okay, so first one is related to envelope detection. So I am writing ED. Okay, it is envelope detection, and the question is, an AM signal is detected using envelope detector. Okay, using envelope detector, the carrier frequency and modulating signal frequency is given as frequency are 1 megahertz and 2 kilohertz. Okay, respectively. And here we are going to identify the time constant. Find the approximate time period, approximate time constant for the envelope detector. Okay, and the hint is given, either the time constant is 0.1 microsecond or 0.2 microsecond or 20 microsecond or 1000 microsecond, which can be written as 1 millisecond also. This 10 to the power 3 into 10 to the power minus 6, it will become as a 10 to the power 3, so it will become as a 1 millisecond. 1 millisecond. Okay, so this is the hint is given. In this question, it is basically related to the envelope detector, in which the carrier frequency and the modulating signal frequency is given as 1 megahertz and 2 kilohertz. Now for modulation purpose, we require two signals. One is modulating signal M of t and one is carrier signal C of t. Now when we are transmitting the signal, it becomes as a modulated signal. Okay. Now modulated signal is an AM, S suffix AM of t, and then we are writing A suffix C 1 plus K suffix A into M of t and cos omega C. Okay, this is my AM signal which I am going to transmit. Then now this AM signal need to be detected with the help of envelope detector. Now last class we have seen how this envelope detector works. There are three cases we have considered. If the MA or the modulation index is less than 1, what happens? If it is equal to 1, what happens? And if it is greater than 1, what will happen? So if it is over-modulated, we cannot reconstruct the original message signal. But the envelope detector will work for the modulation index which is less than equal to 1. So we can reconstruct the modulating signal easily. So that thing need to be identified first. Then we can understand that what is the approximate time constant in this question they are going to ask. So here, modulating signal passes through a modulator in which carrier component is available. Okay, and here after passing through this band pass filter, we are transmitting the AM signal. So this is the concept behind our transmission purpose. But at receiver side, we need to demodulate this AM signal so that we can recover the modulating signal. So here it is given modulating signal frequency. Here the lowest frequency is 2 kHz and the highest frequency is 1 MHz. That means the lower one is 2 kHz. So this is my modulating signal frequency, and carrier signal frequency as it is given 1 MHz. Then now your envelope detector, how it is look like? It is a diode circuit followed by R and followed by a capacitance C. So this is the output we are observing of the envelope detector. So it is Vi of t and this is V naught of t and this is my LP or smoothing filter. Now since this is a particular envelope detector, if it is operating for MA less than 1 or equal to 1, then we can recover our original signal. But if it is greater than 1, only magnitude is available but we cannot recover the original message component. Okay. So here the C and R, these are the two people who decide what will be the frequency range or what will be the condition to extract the modulating signal. Now last class I have given a relation that the time constant means product of R and C must be greater than 1 by Fc and must be very less than 1 by Fm. Okay, this is the condition for envelope detection. If your time constant is greater than the time period of carrier component, then we can easily recover the modulating signal. It will follow the envelope detector. Okay. Similarly, if your time constant is less than the time period of modulating signal, then also we can reconstruct. But if it is greater, we cannot reconstruct, because that reason also we have seen in the previous class, due to which diagonal clipping will be there, and due to tau constant, if it is high, if it is low, what will happen? Those relations also we have seen. So here we need to identify this relation first. So what will be my time constant? So as this question asks, find the approximate time constant for your envelope detection. So time constant means it is a product of RC, and the product of RC must lie between 1 by Fc and 1 by Fm to extract the modulating signal as we are transmitting at the transmitter end. Reconstruction must be done. Okay. So here I can write 1 by Fc is nothing but Tc, which is very less than product of Rc and very less than Tm. Okay. So this time period we can calculate. How we can calculate Tc? So 1 megahertz. 1 megahertz means 10 to the power 6. So 1 by 10 to the power 6 means it will become as a 1 microsecond. Okay, which is very less than Rc. Okay, and then what is Tm? Tm is 1 by 2 kilohertz. So 2 kilohertz means it is 0.5 millisecond, or you can write 500 microsecond for that. So here I will write it is 500 microsecond. So here I can write Tc is equals to 1 by Fc, Tm is equals to 1 by Fm. So 1 by 10 to the power 6 we will get 1 microsecond. Here it is 1 by 2 kilohertz. If I will solve, I will get 500 microsecond. So this is the time period. Now my detector will work between these two time periods because my time constant must satisfy this particular relation for envelope detector. Then, so this indicates that means my time constant must lies between 1 microsecond to 500 microsecond. Now in this question, some options are given that the time constant is 0.1 microsecond, 0.2 microsecond, 20 microsecond and 1 millisecond. So that means which will be our time constant? First, if it is 0.1 microsecond, that means this value won't fall in this particular range. The range is 1 microsecond to 500 microsecond. So it won't fall. Next, if it is 0.2 microsecond, this is also not possible. Third is 20 microsecond. Yes, it is possible. 1 microsecond to 50 microsecond means it is possible. Fourth one, 1 millisecond or 1000 microsecond. But our highest limitation is 5000 microsecond. So that means this is also not possible. So what is our time constant? Time constant tau is equals to Rc is equals to 20 microsecond. So this is the time constant for my envelope detector. If that detector identify a modulated signal in which the modulating signal frequency is 2 kilohertz and the carrier is 1 megahertz, then the time constant of the envelope detector, this Rc, it must satisfy 20 microsecond. If in the option, if it is given as 100 microsecond, then also it is possible because the highest limitation is 500 microsecond. If the option is given as 1.2 microsecond, then also it is possible. Why? Because the least amount is 1 microsecond. So 1.2 to 500 it is possible. So you have to check the range and you have to identify the time constant. So with the help of this relation, we can easily get the time constant for envelope detector. Suppose if I will change this to frequency, my time constant is also going to change. For example, in the same question, if the modulating signal frequency and carrier frequency are changed, let us see what will happen to my time constant. Okay. So let us consider the above one is case 1. Now it is case 2. So as per the given question, it is case 1. Let us consider case 2. Fm is 200 Hz and your carrier frequency is 4 megahertz. Then now our time constant must lie between these two. Time constant of whom? Time constant of an envelope detector. So what is my Tc? Tc is equals to 1 megahertz. So that means it is 0.25 microsecond. Then similarly, what is the time period for your modulating signal? 1 by 200. Okay. So that means it is 0.5 10 to the power 3 into 10 to the power minus 6. So that means it will be how much microsecond? It will come around 500. It is around 5000 microsecond. 5000 or 500? 500 into 10 to the power minus 6. So it is 5 into 10 to the power minus 4. So it will become 1 by 200. 5000 microseconds. It will come around 5000 microseconds. Let us consider 5000 microseconds or 50,000 microseconds. It may come. Okay, 5000 microseconds. So here I will substitute TC 2.25 microsecond less than RC less than 5000 microsecond. For generally I am considering 5000 microseconds. So that means now my detector will operate for a time constant varies from 0.2 microsecond to 5000 microsecond. If I will consider this range, then this won't be possible, this 0.1 won't be possible, but if it is 0.2 microsecond, but it is starting with 0.25 microsecond, that is also not possible, but 20 microsecond is possible and 1000 microsecond is also possible. So the two frequency which can be or two time constant which can be assumed for the design of this envelope detector. For the frequency FM is equals to 200 Hz and FC is equals to 4 MHz. So with the help of this sort of relation, we can identify the time constant of envelope detector. Okay. So this is the first question. So I think so it is clear. Next we will see one more question. So in this envelope detector, this is one relation through which you can decide the time constant, and that time constant depends upon carrier frequency and the modulating signal frequency. So this is one form of question. In exam they may give the AM signal in which it will be written in terms of AM signal, AM equation, cos omega ct and cos omega mt. Cos omega ct, if it is written, means that omega c some value they will give, omega m means some value of modulating signal frequency they will give. From that you could decide what is the time constant. So this is the relation through which you can identify the time constant for your envelope detector. Okay. So next we will see one more question. So second problem, a message signal m of t is equals to m of t is equals to cos 2000 pi t plus 4 cos 4000 pi t. Okay. Modulate the carrier C of t is equals to cos 2 pi fct. Okay, where fc is 1 megahertz. Okay, to produce an EMF. for demodulating, the generated AM using an envelope detector, using an ED, I am writing ED, that means it is envelope detector. The time constant for the detector is RC. Find the range of RC. Find the range of RC, that means you have to identify the range of time constant. Okay? So step by step we will see how to identify this. So first of all, what are the data is given that we have to identify? First one, the message signal is given. Now since it is more than one number of carrier, means frequency component is available, that means I will say it is called as multi-tone signal. So first, M of t, how much it is? Cos 2000 pi t plus 4 cos 4000 pi t. So this is the multi-tone modulating signal. We are discussing about multi-tone modulating signal, and it modulates the carrier, that is C of t cos omega c, or we can write cos 2 pi fc t, in which fc is given 1 megahertz. So this is the data is provided in this question, and this multi-tone modulating signal is going to be modulate the carrier component with a strength of 1 megahertz. So this is my multi-tone signal and this is the carrier signal. Then now how we are going to decide which frequency component is going to modulate? That is the thing when we are identifying the bandwidth. With the help of bandwidth we can know which frequency is going to modulate, or which frequency component will help us to identify the bandwidth, so that frequency we will use to determine the time constant. Okay, because the total bandwidth we are going to transmit, the total bandwidth is called as AM signal. Within that our two upper segment and two lower segment is going to be available, through which we can extract the information with the help of our envelope detector. So how we are going to identify the bandwidth? If it is multi-tone, then we have to multiply the maximum frequency twice of the maximum frequency available in the modulating signal. Now, if it is f max of f1 comma f2, so first of all I have to identify the frequency f1. So f1 is equals to how much? Here it is cos omega 1t and this is cos omega 2t. So f1 is equals to omega 1 divided by 2 pi and f2 is equals to omega 2 divided by 2 pi. So this is the relation. Now omega 1 is how much? It is 2000 pi divided by how much? 2 pi. So that means we will get 1000 hertz, or we can say it is for 1 kilohertz. Then second, what is omega 2? Omega 2 is 4000. So it is 4000 pi divided by 2 pi. So that means I will get 2 kilohertz. Now out of these two frequencies, which frequency is having higher value with respect to other? The second frequency is greater with respect to first. So here I can say F2 is greater than F1. So that means my bandwidth of AM signal will be depend upon this F2. So here I will write the bandwidth is equals to twice of F2. So twice into how much? 2. So that means it is 4 kilohertz. This is the bandwidth of an AM signal, which is a multi-tone, consists of multi-tone modulating signal. So this is the bandwidth. So from this we have concluded that F2 is greater than F1. So that F2 plays a vital role to decide by the envelope detector. He will identify that maximum frequency available in the transmitted modulating signal to identify the FC component, carrier component as well as FM component. Okay. So after modulation, so this is my M of t, this is my C of t, pass through a band pass filter. We are transmitting an AM signal, which is a multi-tone signal. Okay. So now this received AM signal is going to be demodulated with the help of envelope detector. Now envelope detector, here it is asked about the time constant RC, and as we know that envelope detector time constant RC lies between 1 by FC and less than 1 by FM. Okay. Now what is the carrier frequency? Carrier frequency is this. So TC is equals to 1 megahertz. So again here I will say it is called 1 microsecond. Then similarly, what is Tn? Now this Tn plays a vital role. Here we are going to transmit two different modulating signals, but your bandwidth depends upon the higher modulating signal frequency that we have identified 2f2. Now this 1 by Fm is nothing but 1 by maximum frequency available in the modulating signal. So here it is 1 by Fm is how much? It is 2 kilohertz. So it is 2 kilohertz. Okay. Now this kilohertz, if I will take upside, it will become 0.5 millisecond. So that means my time constant will lie between 1 microsecond to 0.5 microsecond. And here in this question it is asked, find the range of RC. So the range of RC, or you can say time constant tau, is lies between 1 microsecond, which is very less than RC, which is very less than 0.5 millisecond. So this is my answer. Okay. So this is my answer. So this is the range. So like this question will come in your exam to identify the time constant for a given envelope detector with respect to the modulating signal and carrier component. So there are the two variations we have seen. One, if the carrier signal frequency and modulating signal frequency for a single tone, and here we have seen with respect to the multi-tone signal. This is the multi-tone signal, and this is the carrier component whose frequency is given is this. Time constant we have identified. Now which frequency we need to use for demodulation, that we have to check with respect to the bandwidth. How we are identifying the bandwidth? Bandwidth is identified with the help of the twice of the maximum frequency available in our modulating signal. So what is the maximum frequency? 2 kilohertz. Because F1 is 1 kilohertz, F2 is 2 kilohertz, so maximum is 2, so bandwidth will become as a 4 kilohertz. Done? Now the maximum frequency available in the modulating signal help us to decide the envelope detector modulating time constant. So that is Tn, this is Fm. we need not to consider this 1 kilohertz, we have to consider 2 kilohertz because the higher frequency is 400 pi is given, that is 2 kilohertz. So maximum frequency is this, so that we can recover both the modulating signal, one for this and one for this. Okay, so this is the complete explanation for this particular question. Done. So next one we will discuss. I will erase this. So our answer is range of RC or the time constant will lies from 1 microsecond to 0.5 millisecond. For what purpose? For these are the analogy or these are the given data. So next question is related to the synchronous demodulator. Okay. So the question is, show that like this type of question may come in your exam. Okay. Show that a synchronous demodulator, or you can say it is called detector. Okay, demodulator shown in figure can demodulate the received AM signal, that is S suffix AM of T is equals to A plus M of T cos 2 pi FCT, regardless the value of A. Means amplitude of carrier. And the diagram is, we are receiving A suffix M, we are providing the carrier is cos omega ct, passes through, output is passes through LPF, and you have to decide what is y of t and what is d of t. D of t is this, y of t is this. So this is the given figure, and you have to determine what is d of t and what is y of t. Simple. So step by step we will see. So since it is a synchronous, we need to synchronize the frequency and phase component of our carrier. Okay, as in the given question, the modulated signal is this. Frequency is available as cos omega c, and at a receiver, this is the figure called receiver. Okay, this is the figure at receiver end. This is the receiver end. So at receiver, the carrier whose amplitude is 1 as it is written regardless the value of A. Let us consider as the given figure it is cos omega ct. Now this frequency and this frequency are synchronized. Then only this detector is called as a synchronous detection. Okay. So now if it is a synchronous detector, what is my first the given data we will see S suffix am of t is equals to A plus m of t cos omega ct. At a receiver, the carrier C of t is cos omega ct. What will be my d of t? D of t is simple multiplication of the modulated signal with the carrier provided by the local oscillator. This is the local oscillator who is providing the cos omega ct. So d of t I will write S suffix am of t into C of t. Done. Now what I will do, I will simply multiply these two components so that I will get A plus m of t cos square omega ct. Now this cos square omega ct you can expand as cos square theta is equals to 1 plus cos 2 theta divided by 2. You have to use this relation. Okay. So in place of theta it is omega ct, so it is cos square b. So next equation I will get it is A plus m of t 1 plus cos 2 omega ct whole divided by 2. Then you need to expand this relation, that is d of t. One expansion you will get amplitude divided by 2. This is the first component because 1 is there. And second, A plus m of t whole divided by 2 cos 2 omega ct. Okay. Now this d of t is available at the output of mixer. Now what is the principle of low pass filter? The principle of low pass filter is its response is limited to the modulating signal frequency. Okay, 0 to FM it will identify. It will pass all those frequency component which lies between 0 to FM, and the higher harmonic component, rather than if it is 2 omega c or it is a omega c or it is a 2 FM, as well as the DC component are going to be suppressed with the help of our this low pass filter. Now this d of t is provided to the low pass filter. Low pass filter we will get y of t. Now this y of t is equals to A plus m of t divided by 2. And this is the higher frequency component, higher harmonic component, it will be suppressed by the low pass filter. Now in some of the book the output will be written in this term. In some of the book it will be written in terms of m of t by 2. That means this component need to be passed through a DC blocker. So this LPF will also help to suppress the DC component. So here A by 2 plus m of t by 2, and this DC component tends to 0. It is suppressed. So that means my y of t is equal okay. So let us consider this is y dash of t and this is y of t. So y of t we will get m of t divided by 2. So it is a message signal we are extracting, but the amplitude deteriorates. Here the amplitude is m of t, it is there, but here the amplitude is reduced by half. So this is the working principle of synchronous detector, in which we have considered that carrier is of strength of cos omega ct. And this is the simple relation. First we have to identify the output of mixer. This is the output of mixer. Here I can write output of mixer. Then output of mixer will elaborated. Solve these equations. You will get one DC component, one modulating signal component, and one harmonic component. So these are the harmonic components. So this harmonic component is going to be suppressed when it is passed through the LPF. Now here I have written y dash of t. Y dash of t will consist of a plus m of t by 2, in which a by 2 is a DC component which is suppressed, and only the message signal m of t by 2 is going to be achieved. So the output of this detector will be m of t by 2. So here I can write y of t is m of t by 2. So this is my answer. So this is a small derivation for synchronous detector as per the given question. Okay. Now next, one more question we will discuss. So next question is, it is related to the envelope detector. Okay, consider the AM signal. Consider the AM signal AC cos omega ct plus 2 cos omega mt. So this is the AM signal. Okay. For demodulating the signal, which signal? AM signal. Okay, using envelope detector ED. Okay, and here we need to find the value of AC, means amplitude of carrier we need to determine. Okay. Now how we are going to identify this amplitude of AC with the help of envelope detector. Now as we have seen that the different relations are available if it is an envelope detector. We have seen that if MA is less than or equal to 1, that means MA less than 1, MA equal to 1. Then only we can recover the original message signal. But if it is MA greater than 1, we will get some sort of signal, but it is not a message signal. It is a only magnitude component, only the envelope we are getting, not the modulating signal. So modulating signal can be recovered with the help of these two conditions. Means your envelope detector will work for MA less than 1 and MA equal to 1 to get the modulating signal. But if it is a over modulated signal, we cannot recover the modulating signal. Only the envelope we are going to identify. Means only the magnitude component we are going to identify with the help of this component. Now, as per the given question, here AM signal is equals to AC cos omega CT plus, here it is cos omega CT is also available because modulated signal. So it is 2 cos omega MT into cos omega CT. I can write AC 2 cos omega MT whole into cos omega CT. So this is the AM modulated signal. Now if AM modulated signal and we can recover the original message component, that means my modulation index must be less than equal to 1. So if it is modulation index is less than equal to 1, that means original modulating signal can be recovered. Now what is MA? MA is magnitude of modulating signal divided by magnitude of carrier signal must be less than equal to 1. So that means this indicates that magnitude of modulating signal must be less than amplitude of carrier. Now here you can see the amplitude of modulating signal is 2. 2 cos omega mt, what is the magnitude? Magnitude is 2. Vm cos omega mt. So Vm cos omega mt is m of t. So this I can write here, this equation S suffix am of t is equals to AC plus m of t into cos omega ct. Done? Now as ma is less than 1, that means magnitude of modulating signal is also less than AC. So what is the magnitude of modulating signal? Modulating signal amplitude is 2. So AC. So here I can write AC must be greater than equals to 2. So this is the amplitude of modulating signal. These sort of questions are also coming in your exam. Here they have given in one form. In other question they may give in terms of this frequency component in multitone signal. Multitone signal, here we have considered only one modulating signal. In other it can consider multitone signal, more than one number of modulating frequency with some other potentials are available. For example, here we have used 2 cos omega and 1. But if it is given 2 cos omega 1t plus 10 cos omega 2t, then we have to consider the maximum amplitude available in the modulating signal is 10. Maximum means the mod of m of t. So mod of m of t will become as a root over of first signal plus second signal, then maximum value will be AC. And AC must be greater than the maximum amplitude in our modulating signal. So this is one sort of question may come in your exam. This is also related to the envelope detection. Now why I have chosen MA is less than equal to 1? The key word is envelope detector. The envelope detector work if for extracting the modulating signal easy manner if the modulation index is less than equal to 1. Okay, this is the key point. With the help of this key point, I have used MA less than equal to 1, through which I have formed a relation that amplitude of modular carrier component must be greater than equals to 2. Okay, so this is one sort of example through which you can understand the principle of envelope detection. Now, one more question we will see. So next question is also related to the envelope detection. Okay. So that is the amplitude modulated waveform, the AM waveform S suffix AM of t is equals to 1 plus MA cos omega MT into cos omega C is to be demodulated using envelope detector. Find maximum permissible value of modulation index. Maximum permissible value of modulation index for which the modulation is possible. And next, also sketch the output of envelope detector for modulation index equal to 2. Okay. So this is the given question. Now, in previous class we have discussed that in the previous example also we have seen that envelope detector will work efficiently if my modulation index is maximum value is 1. Okay, less than means MA less than equals to 1. Then only we can recover the original message signal. So here it was asked, find the maximum permissible value of the modulation index for which demodulation is possible. So what is the maximum modulation index? So maximum modulation index is MA less than equal to 1. Now once again I will discuss the figures so that you can correlate that first case 1, MA less than 1. In this, suppose my modulating signal is this. Okay. If my modulating signal is this, if for MA less than 1, that means my modulated signal will be in this sort of representation and my carriers are available within this envelope. So this is my MA less than 1, means under modulation. Now this AM signal is provided to envelope detector. Now what is the output of envelope detector? Envelope detector consists of a diode followed by a parallel combination of RC circuit. Okay. So if it is output of a diode, because time constant will come into picture, so output of diode means only upper half is available. So upper half is available means my waveforms will look like this. Okay, so this is the output of diode. Okay. Now output of diode will work only for positive half. Then there is a parallel RC circuit is there whose time constant need to be maintained very less than 1 by Fc and 1 by Fp. Okay. Now here again peak to peak charging, discharging, charging, discharging, charging, discharging, charging, discharging, charging, discharging. Now this sort of waveform will come into picture at the output of capacitor, because there is a parallel capacitor is there, and then the output of that means parallel capacitor feed into the smoothing filter. And what is smoothing filter? Smoothing filter is nothing but parallel combination of R and C. So the output of the smoothing filter will be look like this. So this is my output. Now here you can see that the modulating signal and the output of this reconstruction signal are quite similar. So that means we can recover the original message signal if the modulation index is less than 1. Now in another case also we have seen that if modulation index is equals to 1, modulation index equals to 1 means amplitude of a modulating signal and amplitude of a carrier signal both are same. So that modulation index is 1. For this, my modulating signal, let us consider this is our modulating signal. For this modulating signal, my modulated wave will be in this form. It will just touch the 0%. And here my carrier signals are available. This thing we have discussed in the previous class. Just I am recalling all those concepts for understanding what is the maximum modulation index permissible to get the modulating signal. So this is my modulated signal. Now this modulated signal, when it is given to this envelope detector, the output what we will get, first output across the capacitor, because there is a parallel capacitor is available. So in that, like this. So here within this only positive half cycles are available. Like this. Okay. So this is capacitor charging, then discharging, charging, then discharging, charging, then discharging, charging, then discharging, then charging, then discharging, then charging, then discharging. So what will be the output of smoothing filter? So output of smoothing filter will be looking like this, which is quite similar to your modulating signal. So if it is similar to the modulating signal, that means I can recover the original message signal for whom the modulation index equal to 1. So what is the maximum permissible modulation index? So the maximum permissible modulation index is, the condition is MS less than equal to 1. But if it is greater than 1, the envelope distortion will come and we won't recover the original message signal. Okay, so that is the first part. So this is the explanation for the first part. Second, we will see here it is asked, also sketch the output of envelope detector for modulation index equal to 1. Now what is this? Now modulation index greater than 1, that means it is called as over modulation. If it is over modulation, then we cannot reconstruct the modulating signal. Okay, only envelope is available, but no modulating signal we can extract. We will see. So now for second case, if MA is equals to 2, MA is equals to 2 means MA greater than 1. So this comes under your over modulation. Okay, over modulation. Over modulation index indicate what? The magnitude of modulating signal is greater than the amplitude of the carrier signal. So modulation index, what is the relation? The relation is magnitude of modulating signal divided by magnitude of carrier signal. When it is greater than 1, when the amplitude of modulating signal is greater than the amplitude of carrier signal. So let us discuss the presentation. So this is my modulating signal. Let us consider like this. So this is the modulating signal. Okay. Now for this modulating signal, the over modulation case S suffix am of t, we will get so this is the modulated wave we will receive, and while this is MA greater than 1, the envelope distortion will come, in which phase reversal will be taken place, which will contribute the noise, and we cannot recover the original signal. So this is MA greater than 1. This is called over modulation case, and this is called envelope distortion. Envelope distortion, which is indirectly contributing noise to my information. I will lose my information. Okay. Next. Now this AM signal is going to pass through the envelope detector. This will go through envelope detector, and we need to identify the output of this envelope detector. So first, the output of capacitor available in the envelope detector, and then we will see output of the smoothing filter, that is the output of our envelope detector. So output so only this positive half we are going to extract. So this is the first, second, third, fourth, fifth, seventh. Okay, and charging, discharging, charging, discharging, charging, discharging, charging, discharging, charging, discharging. Here also we are maintaining the same time constant. So the output of smoothing filter will be look like this. This is the output of smoothing filter, which is only the envelope. It is not a message signal. Envelope means it is 1 plus MA cos omega mt. This is the only magnitude part is available. Envelope. It is not a message signal. We cannot reconstruct the modulating signal, but it is only giving the magnitude for the modulation index greater than 1. Okay. So up to this we will end up. Next class we will discuss about the generation of DSP-AC signal and demodulation. Thank you.